Good morning, everyone. So we're going to go to the next chapter today, advanced chemical equilibria or advanced equilibria. So I'm going to start now. It's 9 because I can only be with you until 11. And then I'm going to leave you a quiz and a video that answers the first exam. Okay, so we just finished chapter 7 today, and then next week we might go with chapter 8 and chapter 9. Because if we're going to look at the syllabus, will be 7 and 8, and I just found out that I have my a doctor's appointment at 11:30, so I need to be done by 11. Okay, so advanced equilibria. We have started from the previous chapter about the last time that we met for class, that's 2 weeks ago, about equilibrium. And we're going to talk about more details about this concept of equilibrium. Okay, so the thing that we're going to talk about today is something to do with this concept of activity. Now, whenever there is hydration, I don't know if you still remember the term hydration. Okay, hydration is just the formation of solution. Hydration is synonymous to solvation, but when we're talking about hydration, we have water as solvent. So if we have water as the solvent, what do we know from your Gen Chem 1? So this is your, if you're going to look at this, this is your partially negative N, and this is your partially positive N. Now what happened, okay, when we look at the ions and molecules in a given solution? So as mentioned here, ions and solutions are surrounded by an organized sheet of solvent molecules. So if we have a water, it would bind to cut ions through the oxygen atom. So for instance, if we have what? The ever famous Na plus and Cl minus. Okay, so whenever we have an Na plus, most likely it will interact this way with regards to water. Now for the chloride, on the other hand, it will have this kind of interaction. Okay, now what happened to this thing? So you know the concept of this ionic radius. So what do you know about ionic radius? If you have an Na, it becomes Na plus. So what is the size of the Na plus with respect to Na? Is it bigger or smaller? The same thing with chlorine, that becomes chloride. So how is the ionic radius compared to the atomic radius that they have? Anyone? If you still recall your Gen Chem 1?
Wouldn't the cation be smaller than the normal version?
Smaller, and
Yeah.
this will be
Larger.
larger.
Yeah.
Okay, so usually that's the behavior of your ionic radius, but there's still another things that happen when these ions binds with the solvent, which in this case of hydration is water molecules. So it says here, smaller, more highly charged ions bind more water molecules and behave as larger species in solution. Okay? And they said if you have ions, they do not act as independent particles in solvent or water. They are usually surrounded by a shell of solvent molecules. So that means you cannot see Na plus or Cl minus existing as ions. So usually they will be surrounded by the solvent molecules. And if you have water, okay, the exchanges between the bulk solvent and the ion coordinate sites, they are usually quick or rapid. Now, the way that they look at here, the activity here now of the aqueous ions is related to the size of the hydrated species. So what does this mean? Okay, so if you're going to look, so this is ionic and hydrated already. So if you're going to look here, okay, from the original ionic size that you have here, what happened is in the presence of water that serve as the solvent, the ionic radius increases. Okay, so if you have this ionic radius on its own, when it is in the presence of water molecules, it's going to be increased. The ionic radius will increase. So the size and the charge of the ion determines the number of bound waters. So this increase is due to the water molecules that surround them. So as I say, smaller, more highly charged ions bind more water molecules. So we could see here now that the activity that we have is related to size of hydrated species. Okay, so if you're going to look at here, the one that is mostly affected are what? The smaller size. Look at the bigger one. What tells you that you have a hydrated species there? I don't see if you could see the white color there. So see the white color here is a little bit what? More pronounced compared to the one that you have in the bigger size. And see what happened if it is what? More highly charged ion, like a 3 plus. It's a little bit bigger than the Fe2 plus. Okay? So the smaller ions bind more water and behave as larger species in solution. Now, let's try to look at this experiment that was performed if you took Gen Chem 2 here at Pace University, wherein you react Fe3 plus with SCN minus. So usually you're going to form a blood red solution. And if you're going to look at their equilibrium constant, this is how you write them. Okay. Now, as you're going to look at this, the concentration there, quotient or the K value decreases if you add the inert salt KNO3 to the solution. So that is the equilibrium constant is not really constant. Now the question now is why this occur? If I can remember, I think this is one of the post-lab question that was asked in that experiment. So if you're going to recall, this is the experiment that we're talking about. So if you're going to look at here, you have FeSCN complex, okay, resulting from Fe3 plus and SCN minus. Now, why is it that if you add the KNO3, it becomes yellowish. And the explanation that we have there is it shifts to the left. Okay? But that's how we explain it during that time. And the concept that we're discussing today would at least will tell us what's the real reason why this thing happened. Okay? So if we're going to look at here, these are ions, these are ions, this is a complex ion. So we're going to look at how, okay, this ionic strength that we have affect the solubility of the salt. Okay, so let's look on another system that really looks at the solubility. Here, you don't see any solubility. What you see here is just a change in the color. What you see here means that you have less of this, because what is favored is a reaction like this one. The presence of FeSCN 2 plus can be observed due to the presence of a blood red solution, but you don't have a blood red solution here. So that means you don't have FeSCN, or you have less FeSCN. Okay? But to understand what is happening here, we look at the system wherein we talk about solubility. So we go to the system known as calcium sulfate. So when you have a calcium sulfate, if you recall your solubility rules, I think calcium sulfate is one of those that precipitates. But in Gen Chem 2, you learn that the statement that shows that says insoluble is not really insoluble. Okay, it just tells you that the amount of the salt that dissolved is just so low, maybe milligram level, compared to the one that says soluble, which is gram level. Okay, so from Gen Chem 2, you learn that to a lesser extent, some of these insoluble salt really dissolve, but at a very much low amount compared to those soluble salt. So take, for instance, calcium sulfate. So if calcium sulfate, you dissolve it in water, this is the solubility equation. Now, what did they observe here? When they add KNO3, so this is a sparingly soluble salt, it increases the solubility of the given salt. Now, the question is how or why it happens. And the explanation why it happens is also answered by the question how it happens. So they said, when you add ions, which is in the form of potassium nitrate, so what do you have as the ions there? K plus and NO3 minus. It increases the ionic strength of the solution. And if it increases the ionic strength, this increases the charge on the ionic atmosphere. Okay? So, what does this mean? Initially, you only have what? What could be the ions that you have there? Ca2 plus, SO42 minus. But when you add KNO3, you have what? K plus and nitrate. Okay? So, what does this mean? Increases the ionic strength. Anyone? What did the KNO3 did to the system? So the KNO3 both gives you ions. So when you add them, the ionic strength that you have before is just calcium 2 plus and sulfate ion. So when you add KNO3, you form their K plus and NO3. So that means there's an increase in the ionic strength. And Because there's an increase in the ionic strength, there's also an increase in the charge of the ionic atmosphere. So you want to know what is ionic atmosphere, okay? Because the definition, the effect that it says there, the ionic atmosphere attenuates or decreases the attraction between calcium 2 plus and sulfate, thus increasing the solubility. So atmosphere can just be what? The surroundings, right? It's similar to the concept of hydration sphere. Okay? So what will happen here? How does the ionic sphere attenuates the attraction between calcium and sulfate? So what will happen when when you add K plus and NO3 minus? What do you think happened?
Does it make the solution more charged so then the
Yeah,
calcium
it
sulfate
makes the
wants to split
solution more
easier?
charged. But how does the addition of additional ions prevent the calcium 2 plus and the sulfate ion to be attracted with one another again? Hmm? So simply did maybe this one will interact with this one, and this one will interact with this one. What's the reason why they have that interaction? Simply because of their opposite charges. And if they interact that way, what happened? Calcium nitrate is soluble, potassium sulfate is soluble. But the most important thing there is they prevent the calcium from interacting with the sulfate again. So if we're going to look at this ionic atmosphere that was discussed there, okay, it's the region of net positive or negative charge around an ion or cation in a solution. And in a solution containing an inert salt. So what's the definition of inert salt? Anyone? Root word there or main word there, inert. What does inert means there? Anyone? So when we say inert, it's unreactive. Okay? So in a solution containing an inert salt, an anion is surrounded by excess cations, and a cation is surrounded by the excess anions. And the greater the ionic strength of a solution, the higher the charge in the ionic atmosphere. And the net attraction between the cation with its ionic atmosphere and the anion with its ionic atmosphere is smaller than it would be between pure cation and anion in the absence of ionic atmosphere. So that's the one, okay, that explain why there is greater solubility when you increase or when you added an inert material. Okay? So what happened? If an inert salt such as KNO3 affects the ionic atmosphere, it is in the way wherein in the solution, the cation is surrounded by NO3 ions, and the anion is surrounded by the K plus ion. And the net result is a decrease of the attractive forces between the cation and an anion pair. And increasing the ionic strength promotes dissociation into ions. Did you get that? Because we go back to explain now what happened to your potassium thiocyanate. We're going to explain now why this happened when we add that salt. And following the concept that we have just discussed, it only means that this was surrounded by which one? NO3 minus, and this was surrounded by K plus, preventing them from forming the complex ion. So if you're going to add an inert salt, okay, the way it interferes is it prevents your ions from interacting with one another. So here, the addition of the inert salt prevent the ferric ion from reacting with the thiocyanate to form the ferric thiocyanate complex. Okay? So we go now to this concept of ionic strength. So ionic strength, effect of ionic strength on the solubility of salts. So we already discussed that. Okay? So to formally introduce what is ionic strength. So base here, ionic strength, which has this symbol, modified U, is a measure of the total concentration of ions in solution. And if you're going to look at the formula, this is just equals to this one. Ionic strength is equals to 1/2 of the concentration of one of the ion, okay, times, what is C? Anyone tell me what C is?
The concentration of the ion.
That's the
Z.
charge.
Yeah, Z is the
The
charge.
Z, as in zebra. So C is
Okay.
C as in cat is concentration of ion. Z as in what we call zebra is charge on ions. So whether you have a positive or a negative charge, since you're going to square it, it will always become positive. And the more highly charged an ion, the more it is counted. Because if you have only a positive one or a negative one, it's always give you equals to what? When you square them.
1.
That's always equals to 1. But if you have a more highly charged, it will be counted more. Okay? So let's try to see how we determine ionic strength. So find the ionic strength of 0.1 molar sodium nitrate. So what do we do here? So mu is just equals to 1/2. Okay. And then we're going to look at the concentrations that we have there. So I could say the concentration of Na plus times what, this is +1, right?
Yeah, sodium is +1.
And then we add it with the NO3 minus, okay, times, I think I have to make it like times -1 squared. So where do I get the concentration of this? From this one, when they dissociate. So if I'm going to do it, so this will become what? 0.1? Oh no, this is the thing that I hate. Times 1. And then the other one is also 0.1 times 1. So this is just equals to what? 0.1?
Yep, 0.1.
Yep, put 0.1 there. How about the others? Do you get it?
It's pretty simple.
So let's look at the second one, the same thing that we're going to do. Okay? So we have here so I have an Na plus, and the charge of that is also +1. So squared. Okay, and then I have here an SO4 2 minus. So the charge of that is -2. So what I'm going to do now is I'm going to replace it with the concentration that I have. So I have 0.01. Right? And then here I have, how many sulfate do I have? No, this is not 0.01. This should be 0.02. Because I have 2 sodium ions per every sodium sulfate. Okay? And this one, this is still 0.01, but I multiply it now by 4. So what do you get?
I got 0.03.
Everybody got that?
Yeah.
Before we go to the more complicated thing in the last item. So in the last item, you could see there's 2 sources of your ions. So you're just going to put everything together. Okay? And then determine what is the ionic strength. So you have 1/2 of everything. So you put there maybe the K plus times +1 squared. And then you have the Br minus times -1 squared. Okay, and then plus the sodium ions times +1 squared, and then plus the sulfate ions times -2 squared. So that's the whole thing that you have there. And then you're going to calculate them based on the given concentration. So you have here what? 0.02 times 1 plus 0.02 times 1 plus how much sodium ion do you have? 0.01 times 2 and then for the sulfate 0.01 times 4. So what will be the ionic strength here? Anyone? What's the answer?
I got 0.050.
So I got this one, 0.050 molar. So if we're going to look at this ionic strength, okay, that we have here, we could say this is just what? The addition of salt solution increases the ionic strength based on the example that we have earlier.
I have a question.
Sure.
Why does the third bracket with 0.02 moles? I thought that's 0.01 for sodium sulfate.
Which one?
For part C and the third bracket.
This one?
Yeah, 0.02 multiplied by 1. I thought the molarity of sodium sulfate is 0.01 mole.
Yeah, but for every sodium sulfate, you produce 2 moles of sodium ion.
Got it. Thank you.
Okay? So when we have the ionic strength, we could say this is a measure of the total concentration of ions in the solution. And the more highly charged ion is the more it is counted. And you just have to follow it using this equation or formula in solving the ionic strength. Okay? Now, let's go to this concept of activity coefficient. In most of the things that we have discussed, we always have this concept of concentration. Okay? Now, activity coefficient, we could say, is similar to the concentration. Okay? So as I have discussed earlier, activity is related to the size of the hydrated species. So if you're going to look at the activity of a species, C is its concentration multiplied by the activity coefficient. Okay, so when you're talking about activity of the species, this is just activity coefficients times concentration. In the chemistry courses that we have taken, usually we relate activity as concentration. And in that case, we assume that the activity coefficient is equals to what? Anyone? 1. Because if we say activity is equals to the concentration, so it's just concentration times 1. Okay? So the activity concentration coefficient measures the deviation of the behavior from ideality. So that's why we said activity is equals to the concentration, because we assume that it behaved ideally. It is an ideal behavior. Okay? But if you're going to look at the activity, that's another way of looking at the concentration. Activity is a dimensionless quantity. Remember, concentration is usually what? Moles per liter, right? So if the concentration is absolute, means C over per molar. If the concentration of a gas means pressure in bars, activity of pure, solid, or liquid is by definition unity. Okay? And activities must be used when incorporating ionic strength effects on equilibrium calculations. So what does it mean now? We are already taking into account some effects of the other species that we have in a given system. Okay? Because what we have so far at this time is, okay, whatever we have there, that's the concentration. But if we're going to look at it, there are some interactions that happen to them. Okay? So if there's an ionic strength that you have there, the presence of the ions there, other ions there, you have to take into consideration the effect that they have there. Okay? So how are we going to write this activity coefficient? So let's say here, if we're going to write the equilibrium constant expression using activities, this is how we're going to write them. Okay? Instead of what? KSP equals to the concentration of calcium 2 plus times sulfate. This is how we're going to write them. We're going to write them in terms of activity of the calcium 2 plus and activity of the sulfate ion. And that activity is equals to the concentrations times the activity coefficient and the concentration times the activity coefficient. So you see the transition that we have? Instead of writing them in terms of concentration, we're going to write them now in terms of activity. And all the things that you need is to add whatever the activity coefficients that they have. So let's try to do it here. So what's the K that describes this?
KW.
Okay, KW. And you describe KW as what? KW is just equals to the concentration of the product of the concentration of H3O plus times OH minus. You still recall that?
Yes.
The other students?
Mm-hmm.
So how are we going to express this now using activity? So we have here the activity coefficients. Okay? So if we're going to replace this with the number that we have, so how are we going to write this? KW is equals to H3O plus times the activity of H3O plus, right? Times OH minus times the activity of OH minus. Now the question is, what if we want to get the KW based on the given activity coefficients? How are we going to do that? So we know the KW value as what? 1.0 times 10 to the negative 14, right? And all we need to do is replace whatever we have there. So we have here what? 0.83 of H3O plus times 0.76 of OH minus. So how do we determine the new KW now that we have the activity? What do we do? Anyone? This is just a math thing. So if I want to leave this in this form to give me the new K, I just need to divide both sides by 0.83 and 0.76, right? So this now becomes the H3O plus times OH minus. And my new K now, when I try to consider the effect of the activity coefficient, will be what? 1.0 times 10 to the negative 4 divided by 0.83 times 0.76. What do you get? I get 1.58 or 1.6 times 10 to the 16. Did you get the same thing as me?
You said 10 to the negative 16 is what you got?
Is it 16 or 15?
No, let me try again. I usually mess up on my calculator.
No, it's 1.6 times 10 to the negative 14 still.
That's what I got. Yeah, 1.6 times negative 14.
Okay? So you see now the changes that happen if you express your concentration in terms of activity. Okay? Now the question is, how do we get these values? So you have to take into consideration some factors that affect the activity coefficient. So you have here the effect of the ionic strength, ion charge, and ion size on the activity coefficients over the range of ionic strengths from 0 to 0.1. And the effect of each variable on activity coefficient is given here. So see how the charge affect, okay, the activity coefficient. So if your ionic strength is equals to 0, your activity coefficient is usually equals to 1. Right? But as the ionic strength increases, what happened to the activity coefficients? Overall, what happened? If I gave you this question in the exam.
As
So
ionic
looking at the behavior here, as the ionic strength increases, what happened to the activity coefficient?
decreases.
Usually they decrease. And if you look at the ion size or the ion charge, what can you say? The higher the charge, the higher is the decrease in the activity coefficient. Do you get that? How we interpret this given figure? So if you increase the ionic charge, the activity coefficient decreases, and there is a more decrease in it if you have a much higher charge. So most likely it also depends on the size that you have there. Now there are 3 ways to determine the activity coefficients. Okay, one is using the Debye-Hackel equation. Another one is look up in the table, which is given here. And then another one is you interpolate from the table 8-1. So this is the table 8-1. And if you're going to look at here, this is the ionic size that you have, the charges that you have, and these are the ionic strength depending on the given concentration. So look at the given concentration. Are our statements correct that when the ionic strength increases, there's a decrease in the activity coefficient? So look at here, 0.01, then 0.05. From 0.967, it decreased to 0.933, to 0.914, to 0.86. Now, in terms of the charge, so we could compare +1 and +2. Okay, so as you could see here, 0.967 compared to 0.872, 0.83 here, and then you have here 0.45. And I think the size also goes with it. Okay, the smaller the molecule is, the greater is the change in the ionic strength. Okay, so let's try to determine the activity coefficient. So here, find the activity coefficients of calcium in a solution of 3.3 millimolar of calcium chloride. So how do we do this? We have to find first the ionic strength. So how are we going to solve this? Calcium 2 plus times +2 squared, right? And then chloride ion times -1 squared. So I want you to solve it, at least for the ionic strength. And you have to be careful because this is what? Millimolar. So try to solve it. Try to do it on your own. So you have to make sure you put the correct value here. So 3.3 millimolar. So that's how many zero? Millimolar.
3 zeros for most.
So is it how many zero?
Well, it's gonna be 0.0033 for
1, 2, 3. How many zero? 3 or 2?
just two, and 33. Yep, that's a conversion for millimole.
So how much do you get there? What value do you get?
Why is the concentration of chlorine ion
Oh,
this?
we have to multiply this by 2.
Right. Okay. Yeah. That makes sense.
What's your answer? So if we got 0.099, no, 0.0099, because I got 9.9 times 10 to the negative 3. So that means 1, 2, 3. So that you can run it up to what? 0.01. Because what you want to get here is the ionic strength. And then from the ionic strength, what you're going to do? You go back to the table and then find what's the corresponding thing for calcium, right? So where's calcium? 2 plus. There. So that would be 0.01. So you have there 0.675. No, 0.675. So here, we're going to look at the calcium there. Oh, I have to share it again. So you have here the calcium. So the corresponding value there with that ionic strength is 0.675. So that's one way for you to determine the activity coefficient. So that means you need this table with you. Okay. Now the other way is the use of this dy-Haeckel equation. So this was what we call formulated by Peter dy. I forgot the name of the Haeckel. Dy, I was able to meet him personally. Haeckel is a much older guy. So in the dy-Haeckel equation, you relate the activity coefficients to ionic strength using this formula. Okay, so you have there the log of the activity coefficient equals to negative 0.51 times the charge of the ion times the square root of the ionic strength divided by 1 plus, okay, the answer from here, the square root of ionic strength times the hydration radius in picometer over 305. Okay, so they were able to develop this one, and they found out that it is useful if the ionic strength is less than 0.1. And it approaches unity at low ionic strength. So it's a high ionic strength makes the activity coefficient smaller, which is what we have earlier based on the figure that was given or that was shown to you. Okay, so let's try to use the activity coefficient, determining the activity coefficient using the dy-Haeckel equation. So you are asked here to calculate the activity coefficient for the hydronium ion in a solution that is 0.1 molar in NaCl. And the ionic strength is calculated as 0.1, and the size that is given is around 900 picometer. So if you're going to remember, this is the equation that we have, log of the activity coefficient. You have 0.51 times C times the square root of ionic strength, and then you have here 1 plus the length ionic strength over 305. So what do? We replace the value that we have. So we have what? 0.51. What is C? Can we say it's 1?
C is 1. Yeah.
That's a C squared. So that's 1 plus. And then mu is 0.1. Then divided by 1 plus. So you have here 900 square root of 0.1 divided by 305. So what's the value that we get here? Square root of 0.1 times 1 times 0.51. So that is negative. We'll do it step by step. So what's the value that you get in the numerator?
I got for the numerator, I have negative 0.161.
Now, the one in the denominator, anyone? What do you get there?
I got 1.93. 3. 1.923.
So if we have that 0.161, I just calculate all the values that I have seen there in 1.933. So I'm going to get around negative 0.0834, right? But remember, this is log. So to get the activity coefficient there, so I get around 0.82, 8252 or 83. So 0.8252. So this is around 0.83. Okay.
I have a question, Professor.
Okay.
So I noticed in the 8.1 table, it specifically mentioned that those activity coefficients are specific to being at a temperature of 25 degrees Celsius.
Yep.
Do those activity coefficients change much when that temperature
Yeah.
changes?
It's most likely changed.
Okay.
Now the last one, I'm just going to show you right away here because remember there's 3 ways to do it. One is looking up the table, which we did first, and then the one that we just did, which is the Debye-Huckel equation. So the other one is just interpolate from table 8-1. Okay. So what does it mean? So the example that you have here, I have here is, let's say you're given the X value. Okay. You're going to plot it, and then you're going to determine what's the corresponding value on it. So this is a typical using graphing method or graphical method. So let's say you're given the value for X as 10 and 20, and then they have a corresponding Y value. Okay. So you are asked what will be the Y value you're given an X. So this is just an example of, let's say, a slope, or how you solve the slope thing. So this is how they do it before. Okay. So if you have here, this is the corresponding XY value, 10.67, 20.83 for the Y value. So what will be the value when X is equals to 16? So the way that you're going to do it is you use either one of them. So here he used the larger value where X is equals to 20 and compare it with X equals to 16. So they get the corresponding Y value that they have there. And they end up with this one. So these are the different ways to determine the activity coefficient. So if we're going to look again about the concept of the activity coefficient, we could say this is summarized in this slide. As the ionic strength increases, your activity coefficient decreases. The activity coefficient approaches unity as the ionic strength approaches 0. So what does it mean? Unity, usually that's 1. And we saw it in the figure that I'm going to show after this slide when I say this one. So when ionic strength approaches 0, Okay, your activity coefficient approaches unity. Unity is just equals to 1. Now, as the magnitude of the charge of the ion increases, the departure of its ionic coefficient from unity also increases. So activity coefficients are activity corrections are more important for ions with a charge of plus or minus 3 than for the ions with a charge of plus or minus 1. And the smaller the ion size, the more important activity effects become. So this is just the summary that we have so far about activity coefficients. Okay. Now, how does the activity coefficient affect the non-ionic compound? Because what we have discussed so far are just what? Ionic compound. Why ionic compound? Because we deal with the charged ions, the cations and the anions. So we all know cations and anions, when they form, they become ionic compounds. So what happened if you have non-ionic compounds, like the neutral molecules, the covalent compound? So neutral molecules such as benzene, acetic acid, and maybe sugar, they have no ionic atmosphere because they have no charge. And to a good approximation, their activity coefficients are unity when the ionic strength is less than 0.1. So we can assume that the activity of a neutral molecule is equal to its concentration. Okay? So let's try to solve this one. So I'll try to give you maybe 5 minutes how to approach this one before we solve this one. So try to solve it in 5 minutes. And then we'll try to solve it, okay, using the concept that we know. So this is what? What concept is this? That's the concept of KSP. So I'm going to give you the KSP value for the one that you're solving. There's 3.2 times 10 to the 11. So try to think of it how to set it up. Okay? Anyone have an idea how to do this?
Um, so could we start by writing the chemical equation?
Okay.
Yeah.
So how do we write that thing?
Would be calcium fluoride plus sodium fluoride, or no?
No,
Oh, okay, okay.
should be like this. That's the starting point because this is what? A solubility. And if you're going to write the solubility KSP expression, you will have like this. But you're going to change it, right?
Right. We need the activity coefficients.
So calcium 2 plus times the activity coefficient of calcium 2 plus, and then F minus squared times the activity coefficient of F minus squared. So the thing is, I went back there earlier. You need to determine this value. So if you're going to look at this, look at the concentration, 0.05 molar NaF saturated with calcium 2 plus. So the solubility of calcium 2 plus is so small, so the concentration of F minus is 0.05. So you have to look at what's the concentration that we need to use here. What's the ionic strength that we need to use here? So since fluoride is the only one that is given there, so we're going to use this as 0.05. There's just a 1:1 mole ratio that you have there. So we go at 0.05. I think you have this one and this one. 0.81 and 0.485. So if we're going to look at here, what else do we know? What value do we know here? 3.2 times 10 to the negative 11. We don't know the calcium 2 plus, but we know this one. That's the 0.485. Do we know fluoride concentration? It's that one. And the last but not the least, the 0.81. So analyze and ask, because you already set up how to answer it because you only have one unknown. And that one unknown is the one that you're looking for. Question? So where did I get this? That's the given KSP. 0.485, that's the activity coefficient at ionic strength 0.05 of calcium. 0.05, that's the concentration of your fluoride coming from sodium fluoride. And 0.81, that's the activity coefficient that you have there. So if you're going to solve that, what is calcium 2 plus equals to? 3.2 exponent negative 11 divided by 0.485 times 0.05 squared times 0.81 squared. What do you get? Anyone?
I get, with sig figs, I have 4.0 times 10 to the negative 8 molarity.
How much?
4.0 times 10 to the negative 8.
How about the others?
Yeah, I got the same.
Wait, really? I got 1.26 multiplied by 10 to the negative 11.
I got 4.0 times 10 to the negative 8. So I just have that. And then I divide everything that I have on the other side. 485 times 0.05 squared times 0.81 squared. That's the concentration that I have. Okay? So how are we going to apply it on another concept that you have learned before? pH. So when we measure pH with the pH meter, we are attempting to measure the negative logarithm of the hydrogen ion activity, not its concentration. So what does it mean? When we have the pH equals to negative log of H plus, it is really negative log of the activity of your H plus, or the negative log of H plus times the activity coefficients of H plus. So calculate the pH of water containing 0.1 molar KCl. So how are we going to solve this? How are we going to use the activity coefficient there? So we could do the KW as a start. So what do we know about the KW?
1.0 times 10 to the negative 14.
So yep, so H plus times the activity coefficient of H plus, and then OH minus times the activity coefficients of the OH minus. And then we can look at the values of this, because what is this? What information we can get from that? Anyone? Why do you think that 0.1 molar KCl was given? What is the basis for that? So I'm putting you here. So what do you think that 0.1 molar K plus serves us? That is your ionic strength. So that means the value of the H plus and the OH minus that you have will come from that 0.1. So you have the 0.83 and the 0.76. That's what it means. Okay, because you might ask yourself, what does it mean? You're not going to use the KCl. Okay, the KCl is just the ionic strength that you given there. So if you have this 1.0 times 10 to the negative 14, I could suggest you just divide it right away with the 0.76 and the 0.81. And you have there the H plus and the OH minus, because those are the respective values of the OH minus and the H plus. And I think earlier we already have get the value over here is around 1.4, am I not mistaken, or 1.6?
1.6.
So all you need to do now is get the value of this. What's the x? So if that's 1.6 times 10 to the negative 14, so all you need to do is get the square root of that. So you have here 1.26 times 10 to the 7. So that's the concentration of your H plus and OH minus. So what can you say about the concentration of your H plus and OH minus? Anyone? Is it less than or greater than 1 times 10 to the negative 7? Because the question that I will ask you, is that the value that we're going to use for the negative log? Or we're going to use it and multiply it with the activity coefficient? Remember, what's the one being asked? The pH. So are we going to get the negative log of this right away, or we're going to multiply it with another value? Anyone?
If we multiply this by the activity coefficient, won't it just give us 1 times 10 to the negative 7?
No, we can look at it. Okay, because remember, this is just what? This is just the H plus. We don't have this one. Now the one that we need is this whole thing. So to get the pH, we have to get it in terms of negative log 1.26 times 10 to the 7 times 0.81.
Oh, I see. So okay. So the 0.81 doesn't go in the log function. It's multiplied afterwards. I see.
Did you get that? Anyone?
Did you write a value down?
So you're just going to what we call get the product of that and then get the negative log, because that's the one that's being asked.
So we're taking the log of the product, right?
Yeah.
That's what we're doing? Okay.
So that is equals to what? What's the pH that you get? Anyone?
I got negative 6.99.
You're gonna have a negative.
Oh, sorry, no negative. That's my bad. Sorry, no negative. 6.99.
Others?
I got the same thing.
1.26 exponent 7 times 0.81 negative log. Negative log 6.99. Okay, question? Question? So let's continue. So let's try to go on the systematic treatment of equilibrium. So the systematic treatment of equilibrium is a way to deal with all types of chemical equilibria regardless of their complexity. After setting up general equation, we often introduce specific conditions or judicious approximations that allow simplification. So you write as many algebraic equations as there are unknown species in the problem. And these equations are usually generated by writing all the chemical equilibrium conditions plus two more, the balances of the charge and of the mass. And there's only one charge balance in a given system, but there could be several mass balances. So this is a new way of solving problems, okay, especially those system of equilibrium. So what is this charge balance equation? So when we have this charge balance equation, this is an algebraic statement of electron neutrality. So what does this mean? The sum of the positive charges in solution is equal to the sum of the negative charges in the solution. So summation of positive charges should be equal to the summation of all the negative charges. And the way that you do this, you multiply concentrations by the charge. H plus and OH minus are always present. Why? Because the system is always in aqueous solution. So if you have calcium, you're going to multiply it by the charge 2 times calcium 2 plus. That is equal to the positive charges. So if we're going to have an example here, if we write the charge balance for CaCl2, this is how it looks like. Okay, because you have what? Ca2 plus, Cl minus, 2 of them. Okay, or you just put this 2 and then the H plus and the OH minus. So if you're going to group them, so these are your cations and you have to multiply this by 2 because you have a charge of 2 plus. While the other one you have chloride and the hydroxide. So that's how you do the CBE. Okay. So let's try to work it with this one. Write the charge balance for a solution containing all these species. So how are we going to write it? So what do we do with this? This and this. They are what? What are these three? Is there another one aside from these three? They are? Anyone? What do you call them?
Neutral.
Neutral. So what do we do with the neutral? Are we going to include them in the charge balance? Yes or no? Anyone? Roll call. Yes or no? Are we going to include them in the charge balance equation? Yes or no?
No.
Okay. How about the others?
No.
Roll call. Put your answer in the chat or say it. Yes or no? Are we going to include them? Okay. The answer is no. Okay. So they're there, but you're not going to include them. So how are we going to write now the charge balance equation? So we follow all of the positive on one side. So we can start with the H plus, okay, plus, what's the next one? So how do we write the Fe3 plus? We put the 3 there and the Fe3 plus. Why 3? Because you multiply it by the charge that it has. So for magnesium, you have 2 times magnesium 2 plus. And last but not the least, ammonium ion. And this is equals, now you start with the negative one. The hydroxide plus the perchlorate plus, so how are we going to write this one? 3 times FeCN6. So that's your pericyanide. Then plus the Cn minus. Any more? So that's your CBE. That's what we call CBE. Charge balance equation. Okay. Now, it was also mentioned there that we have the other equation, the mass balance equation. So also called the material balance. So this is a statement of the conservation of matter. So the mass balance states that the quantity of all species in a solution containing a particular atom or group of atoms must equal the amount to that of atom or group of atoms delivered to the solution. Okay. So later on, when we do the systematic treatment, we need to find, or we need to show both the chemical balance equation and the mass balance equation. So how do we do that? So let's try to look at a specific example. So I type in here how you're going to do that. So for instance here, relate the total mass of a species in terms of the others and the formal concentration. So write the mass balance for 0.1 molar sodium sulfide. So what do you need to consider here? Your sodium sulfide dissociate to give you 2 sodium ion and a sulfide ion. And the way that you're going to write them is this way. This is your what?
CBE.
Okay. You cannot say that's your CBE. Why? Because you don't have this species. Remember, you only have one CBE, but you have several MBE. So this is the MBE for this specific species. Okay? So for every concentration of your sodium plus, you have what? The total sulfide. So why is it described as this one? Because there are other species of sulfur coming from S2 minus. It can be this one, or when it reacts with water or one H plus that you have there, it will become like this. If you react with 2H plus, okay, it will react like this one. Now, what can we say about it is it's equals to 0.1. Because that's the amount of your sulfide. Okay? So you have to remember that when they dissociate, there can be interaction with the other ions that you have. Because you might say, oh, I thought this is the only one that is present. Ask yourself, where does this species came from? Why do I have to consider them as equals or a contributor to the total sulfide? Because they form from the sulfide that was available in the solution that reacted with the H plus that is also available in the solution. So what does it mean? Your sulfide is not just all sulfide. It reacted with the hydrogen. Okay? So they contribute also in terms of the sulfide. They're just in the form of the hydrogen sulfide, the HS minus or the H2S minus. That's what it means on this what we call mass balance equation. Now, the thing that we need to remember in the systematic treatment of equilibrium, you have to write the pertinent equilibrium expression as well as the charge and the mass balances. And then be sure that you have as many equations as the unknowns, and then solve the concentrations by using algebra with approximation or spreadsheets with the solver routine. So mostly we're just going to use the approximation. Because in the solver, it's a software, okay? We estimate the number of unknowns minus the number of equilibria, so it will give us the initial PC values, and then let the solver find the PC values and the ionic strength that minimize the sum of the squares of the charge and mass balances. And the ionic strength value is a byproduct of the optimation. So for instance, if you have this thing, you ask find the concentration of the species in an aqueous solution containing 0.01 mole of ammonia in 1 liter. How are you going to solve that problem? So maybe you can use the reaction of the ammonia plus water, giving you what? NH4 plus and OH minus. So what is this? What's this K equal to? Anyone? What K do you get from this reaction? This is Gen Chem. So NH3 reacting with water to give you NH4 plus and OH minus. What do you get there? What K is that? Anyone? You didn't learn anything from Gen Chem? What K value do we have if we have this reaction? Anyone? Maybe I have a roll call here and then preserve the thing. So what it is? Ka, Kb, Kw, Ksp, Kf, Ki. That's Kb. Why is it Kb? Because you have that. That's the one that tells you it's Kb. If it's Ka, you have an H plus or H3O plus. So that's one of the reaction that you have. That's the first one of the equilibrium that you have. The second equilibrium is just your water dissociating to give you H plus and OH minus. So what K do you have there? You have your Kw. So if you're going to solve the problem here, what's your goal? You have to find NH3, NH4 plus, what else? H plus and OH minus. You're not going to solve, but at least if you have a problem like this, you know what are you're going to look for. So find the concentrations of the species. So you have their ammonia. So what are the other species that you can have there? So the ammonium ion, because it can react with the H plus. Since it is an aqueous solution, you have there an H plus. You have there an OH minus. Okay, so let's try another one. It's just a continuation of what we have done. So we started with this. So the pertinent reactions that we have is these two, the Kb and the Kw, and then the charge balance. So we can have it like this. NH4 plus and H plus. We don't include the NH3. Now the mass balance, we have here NH3 plus NH4. So that's equals to 0.01. And that's usually their formal solution or formal concentration. And then if you're going to look at the equilibrium expression, this is what you will have. And this is the only time you have this activity coefficient. And then you're going to count the equations and the unknowns. So you have how many? 4 equations? 1, 2, 3, 4. And you have what? 1, 2, 3, 4 unknowns. So you have enough information to solve the problem. Okay? Now you can solve the problem. So if we summarize the problem that we have there, here is how it will look like. So you start with the CBE. So you have NH4 plus and H plus, that's your positive ions. And then on the other side, you have the hydroxide. And then what you're going to do, you're going to substitute this expression with Kw over Kh plus. Where did you get that? From this. So you put this on one side. So you just divide both sides by H plus. And that's what the one that you have here. And then you solve for the ammonium ion. So what you do, you isolate the ammonium ion on this side. So you just transpose this. You subtract both sides by H plus, as shown in this equation here. But the thing is, the mass balance is what? NH3 is equals to F minus NH4 plus. So that means you have to put it here. So you're going to replace the NH4 plus with the Kw equals to H plus minus H plus. So you end up with this expression here. In the next meeting, we're going to solve a problem like this. But as you could see, there are common expression that means it can be simplified. But if you're going to use Excel, you can follow the thing, okay, using the command that you have here. And whatever is the one that's changing here, the formula, or the formal concentration, you should be able to get the value that you have there. But usually I don't ask my student to do this thing. I want it the old way, because that's the one that we're going to solve using how to get the pH of intermediate strong acids and strong base. Okay, so you can do the problem solver using that one. So once you have it, you can just input the value that you have there, and it will give you the value that you are looking for. Okay, so we're not going to do anything of this for now, but next meeting, when we go to the intermediate pH, we're going to solve that thing. So the one that I asked you to at least, the one that you know, is at least how to set up, okay, the systematic equation, what you're looking for, and what the important thing that you should have learned by today is not all concentrations are at ease. Okay, usually it's much better to express activity rather than concentration. So, questions so far? Question? Anyone? So I'm trying to put the quiz. Question? Anyone?
No.
So I still have 15 minutes here, although this is the thing that I want you to do. So there's a video on the answers to exam one. Why is it poster? Exam one thing. Okay, posted. It should be posted, not poster. It's not responding. So there's a video on the answers on the exam one that's posted. There's a quiz that you have 2 items. And then you wait for an email by tomorrow regarding the Wednesday lab. If you didn't receive any email, that means we will proceed on. So anyone who wants to do it aside from its schedule? Anyone? For those who did the experiment last time?
Are you
And
asking
then,
who's coming into the lab for Wednesday?
hmm?
Were you asking who's coming into lab next week or this week?
No, this week. The
Oh,
one,
I said I come this week.
the
Like,
one that was working last week.
yeah, I said I would come in.
Oh, you're the one. Yeah, okay, I forgot. Okay. But you have to wait about the email for tomorrow because I'm awaiting something.
Okay.
So if that test will not be good, we might not meet.
Okay, sounds good.
It's not me, it's my daughter.
Yeah.
Okay, so if we, because she was asked, I had to fetch her last week. So we are awaiting for the results. So if ever that goes our way, so I will not be able to come to the campus. But if it's okay, then I will be there. If you don't receive any email, that means all systems go. Okay? You if ever we're not going to meet on Wednesday, you should get an email.
Okay, sounds good.
Yeah, the earliest is tonight. The latest will be today because they gave us the results, but it doesn't show if it's positive or negative. So I have to call the doctor. What does it mean? Okay. And the quiz is until 12 noon. So there's two questions there. It's a short one. One that deals with the ionic strength and the other one maybe a pH similar to what we have discussed earlier. Now, I think I'm trying to see. No, I think we just do it next week. So next week, we try to do acid base, the monoprotic, and then whatever time will allow us to go on the polyprotic. And I also like to schedule our exam because what happened is the coverage of the exams will be until the next chapter that we're going to discuss next week. So do you want it to proceed on the 19th or do you want to do it on the 26th? Because if we're going to look at the syllabus that we have, it is scheduled on the 19th. So that means 2 weeks from now. Okay? And we're going to be done with the coverage of it by next week. So I want you to tell me if you are okay with the schedule that we have or we're going to move it. So everyone is answering, unlike before, no one is answering. And everyone is answering for longer time.
Does that mean we'll on the 19th we'll have class, but the information will not be?
You what we could decide on the 26th, then we're going to have class on the 19th.
Right,
It's
but the
always like
information on the 19th won't be on the test on the 26th.
No,
correct?
because
Okay.
the coverage that we have for the exam is the monoprotic acid next week, but we're going to go with polyprotic already. Okay. I have not looked at the average of the first exam because it's 2 portions. So I have not added yet the 2 portions of the exam. Okay. So question.
Is that 8.1 table, is that posted on Blackboard somewhere?
No. It is in your PowerPoint slide. And remember, when you take the exam, you have open notes, so you can always access them.
Okay. Okay.
Question? So prepare, I would suggest read something about the pH that you did before, because it's almost like that, but with a much deeper discussion. Why 1 times 10 to the negative 8 molar of HCl will not give you a pH equals to 8. So there are systematic treatment that we have next week. In fact, I just prepared this to you for that one. So if I don't have any doctor's appointment today, we should have continued with the acids. Okay, but that's the only schedule that I have, and you know it's very hard to get a doctor's appointment. It will take you around what, 3 months before you can get an appointment. Okay, so take the time that you have to do the quiz and watch the answers to your exam 1. There's a video that is already posted in the Blackboard. So any more question? So if none, stay safe. See some of you on Wednesday.
Thank you.
What happened to this one?
Professor, I wanted to ask